Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. Now we're going to look briefly at some of the many applications of the Bohr model. I'll remind you again that it can be found, copy of Bohr's paper can be found in the original scientific literature, and you probably will need to look at that in order to successfully complete the homework. Plus, and I'll try not to keep saying this over and over again, if you read some of Bohr's original work, then you'll be a step above most physicists who have never done so. They've only read it by people, read of his work by people who've interpreted it. So it's a chance to do something original and creative, in my opinion. Okay, so here's Bohr's energy expression once again. So reminding you, R infinity has the dimensions of inverse length. H bar c is energy times length. N is an integer. And so the basic idea that Bohr had was that these define a system of stationary states, but those stationary states can be disturbed by the electromagnetic field, which can cause transitions. So absorption of a quantum of light can either increase the energy of, raise the electron from a lower to a higher orbit, or emission of a photon can cause an excited state to fall to the ground state. And this idea is still the essential part of quantum theory. The main point is there is fundamentally a lowest state. So in the fullness of time, things will radiate down there. So these are the expressions that one gets for the inverse wavelength. This is why the Rydberg constant is expressed in this strange unit of inverse meters. It comes from the fact, it's in some sense a historical artifact, that the wavelength of light is something that was very easy to measure by diffraction interference experiments. Frequency, on the other hand, is hard to measure directly even today. So the inverse wavelengths of the light are given by this simple formula. So for the infinite nuclear mass, it's just a Rydberg constant divided by these integers. For finite mass, which is something we're going to talk about momentarily, there is a factor of the value of the reduced mass divided by the mass of the electron. So these famous lines, seen both in emission and absorption, the Balmer series, the visible part of the spectrum of atomic hydrogen, were all explained by the Bohr model. Furthermore, there were other lines that were known at the time in the infrared, the so-called Paschen series, and Bohr also applied his model to helium plus, where you change the value of Z, and now you get predictions of where the lines of helium plus should be. And so in the paper that we have available on in the additional materials, he shows that he can explain all the known lines of hydrogen, and then also explain the so-called Pickering series lines as being lines of helium plus. There was some uncertainty at the time as to whether many people thought they were for hydrogen. Then immediately following Bohr's work, within early the next year, Lyman, famous spectroscopist at Harvard University, looked in the far ultraviolet region of the spectrum. It's a very difficult technological region. It hadn't really been explored previously. And he found lines with N1 equal to 1. That's the lowest value of N1. So N1 must be greater than or equal to 1 in Bohr's theory. So he found another series. 1922, the series with, so N1 equal 2, N1 equal 3 were accounted for at the time. N1 equal 4 was discovered 1922, shortly after, when the N1 equal to 5, and so on. They just keep going and going and going. At some point, they stopped naming, actually not at some point, at N equals 6, they stopped naming these series after their discovery because it became appreciated there's an infinite number of these series. Indeed, here's a fairly recent paper that shows just how striking this phenomenon of the Bohr-like series is. These are absorption lines seen. So there's this an interstellar cloud that is between us and the supernova remnant Cassiopeia A. And this is a spectrum. I don't know if you can read it that clearly here, in the radio frequency region. So these are numbers like 25 megahertz. And you see this regular series of absorption lines, all very sharp, and they satisfy the Bohr formula. But now the values of n are not, of the order of 1, but range up to about 1,000. Now, if you recall, the radius in the Bohr model goes as the square of the principal quantum number. So these are atoms that are 1 million times larger than hydrogen. They're the size of bacteria. And so this relationship, the Bohr frequency, from what you've seen now, it's observed to hold over 8 decades of frequency. This is sort of the Lyman alpha region, optical frequencies, down into radio waves. So it's a great unifying concept, and even though, as we'll see, or as you must know, the Bohr described things purely in terms of the classical orbit. He didn't have the essence of quantum mechanics in terms of the superposition principle and the existence of a wave function. Nevertheless, it's an extremely valuable mnemonic and organizing concept. Now I want to mention another aspect of the Bohr model, which is very important in a fundamental discovery in nuclear physics, the discovery of the heavy isotope of hydrogen. So as of this year, 1931, which was 20 years after the Bohr model approximately had been articulated, matter was thought to be made, atoms were thought to be made of protons and electrons. A neutron was not known, but there was this curious phenomenon that many elements had constituents that had slightly different masses. They were chemically similar, but they had slightly different masses. And this is a plot made by a man named Harold Urey, great chemist, which showed the filled dots are the known isotopes known at the time, and he perceived a pattern here that led down to the possible prediction of isotopes that had not yet been observed. There's some other clues, and actually there's a in the supplementary, in the additional materials, there's some guidance to those discoveries. Those are these two contributions: the discovery of deuterium, which is a collection of the original papers, and then a sort of a simplified account written for a professional association journal, which is a summary account of how deuterium was discovered by Urey. I should mention that at the time, virtually all of the isotopes that had been discovered by mass spectrometry, in which you put particles through a combination of crossed magnetic and electric fields and find a deflection that is dependent upon the charge to mass ratio. In the case of hydrogen, there's a stable molecular ion, H2+, which has the mass of 2 expected, 2 units of proton mass that would be expected of the heavy isotope of hydrogen, and the same charge. So, and there's a lot of interference from the molecular signal. So there was no conclusive proof of the existence of heavy hydrogen. So Urey had the idea of looking for this heavy isotope of hydrogen in the optical spectrum of atomic hydrogen. And here is how he states his idea in this is taken from his Nobel lecture of 1934. Bohr's theory, given some 20 years ago, permits the calculation of the Balmer spectrum of the heavier isotopes of hydrogen from this spectrum of hydrogen by the well-known theoretical formula for the Rydberg constant. So even though by this time, 1934, we had Schrödinger mechanics, and Urey was the first American author of a monograph-type textbook on quantum mechanics, very familiar with the subject. He preferred to describe to the general audience the plausibility of his idea in terms of Bohr's well-accepted theory. Now, basically, the difference in the spectrum of a heavy isotope of hydrogen from regular hydrogen in the Bohr theory can just be traced to that the reduced mass difference. So in the online quiz, you get a chance to think about that. So no one had seen a heavy isotope of hydrogen. Urey thought it might be detected in the optical spectrum of atomic hydrogen, but how to prove that decisively? He had the idea of taking large quantities of liquid hydrogen, cryogenic fluid, evaporating the liquid, in the process of evaporation, presumably the lighter isotope will evaporate more rapidly, and so the heavier isotope will be concentrated in the residue. So he recruited a man named Ferdinand Graf Briquetta, who was the United States' leading expert in low-temperature physics at the time. He was the first person to produce liquid helium in the United States, and so Briquetta carried out this distillation process. You can read about it in the summary article if you're interested, and produced a sample in which it was possible to find the evidence for the heavy isotope hydrogen. So this is an emission spectrum. It's from in this particular figure, it happens to be from the Balmer beta line in this spectrum that we've been talking about all this time. And here's the central peak. So really, this peak, continues up off the scale. And now here is the prediction from the Bohr theory of where an isotope of mass 2 should be. And you see that these three curves are spectra taken under different hypothetical concentration of the heavy isotope. And so that the predicted feature grows as expected. There's no evidence for a mass 3 isotope. There is a mass 3 isotope, tritium, but it's unstable and has a very low abundance. So this is a nice application of the very simple reduced mass picture provided by Bohr, the discovery of a substance that in 1931 no one knew it existed,